Hi there, my name is Julian Gordon, although I normally go by Alex, and I'm interested in becoming a chemistry mentor for this upcoming fall 2018 semester at UNC-Chapel Hill. I know we're a bit short on time here in order to keep the video between 3 to 5 minutes, and so I'll just briefly discuss why I want to be a mentor, as well as why I think I'd be effective for the position. Now, to begin, I really want to be a chemistry mentor for two primary reasons. The first is that I love to help people. I was a chemistry mentor last semester for Dr. Ostel's analytical chemistry class, and I found that there were few feelings more fulfilling than having someone come to you worried and concerned about their grade and the course content and leaving you feeling a lot more invigorated and confident in their abilities. It's a fantastic feeling, and I love to do it more. The second reason is that I love chemistry, and I really want to do more of it. And although I got A's in all my classes at Chapel Hill, and specifically the chemistry classes, I believe that there are fewer ways to truly master content than to teach it. And so between loving chemistry and wanting to learn more about it and wanting to help people, I thought chemistry mentoring would be for me. With regards to why I think I'd be an effective mentor, the first one is experience. I'm very capable of doing it. I'm a straight A student at Chapel Hill, and I have experience having done chemistry mentoring last semester in teaching students. And so I know the value of being patient and being able to explain ideas in different ways, to reach out to students with different learning styles. I know what it takes to be a mentor, so to speak. And the second reason is simply that I love to do it. I believe that in order to do a job properly, it not only takes capability, but also passion. And I have the passion to be a mentor. I love to help people. I look forward to teaching students every day. I looked forward to teaching students every day when I was a mentor with Dr. Ostel. And so I anticipate doing the same thing this semester. And so without any further delay, I'll get into how I would solve a potential problem if I were to explain it to a student.
Okay, you'll have to excuse my recording situation. I don't have a whole lot of equipment, so I'm just kind of making do with what I got. So I'll be explaining this problem as if I were to explain it to a student approaching me for help. So here we go. The question reads, which of the following will not have a dipole moment? And we have chloromethane over here, dimethyl ether, methylene chloride, and carbon tetrachloride. So first we have to understand what exactly is a dipole moment, and it's relatively simple. A dipole moment is essentially a moment of polarity in a molecule, which means that overall the molecule is going to be polarized in one direction or another. This could be due to a number of things, but the main thing to keep in mind here is electronegativity. Remember that electronegativity is basically an atom's tendency to absorb, to take in electrons, as opposed to lend them out to something else. So for example, if we were to draw out a periodic table, the general tendency is for electronegativity to increase as we go up like that, meaning that atoms around here are more electronegative than atoms around here. They want those electrons more. So if you pair them together, this one's going to take the electrons from this one in a covalent bond situation. Covalent bond situations are exactly what we have over here. So we have, with regards to our chloromethane here, we can draw it out because that's the best way to kind of consider this. We have our CH3 connected to a chlorine. Since we know that chlorine is a whole lot more electronegative than carbon, and hydrogens you can just kind of leave out of the equation because they don't really matter a whole lot in this context. Think of it just more of a methyl group. Chlorine is a whole lot more electronegative than that, so we're going to have a net dipole going this way, and that's all there is to it. That one's clearly polarized, so it does have a dipole moment. So that cannot be our answer. With B, and this is the other thing, electronegativity is important, but it's also important is geometry of the molecule. So in the case of B, it might look like on paper as it's written here that we're going to have the dipole moments go like this. And you might say those will cancel each other out, ultimately resulting in not having a polarized molecule. However, in these cases, it's going to draw it out. So we'll have our CH3, our methyl group, connected to our oxygen, connected to another methyl group. That'll ultimately make our ether. Now if we look at it, because this is the actual geometry of the molecule, we'll see that we have a dipole moment going like this and a dipole moment going like that. Rather than cancel each other out, they'll create a net dipole moment going up like that, which means it does have a dipole moment. So that can't be our answer either. So geometry and electronegativity are things we have to keep in mind. With regards to our methylene chloride here, we can draw that one out too. We have our carbon connected to two hydrogens and also connected to two chlorines. As in the previous case, we'll see that we have a dipole moment going this way and a dipole moment going this way. So altogether, the whole entire molecule is polarized in that direction. So that can't be our answer either. However, with letter D, we'll see that we do have chlorines and carbons, so you might think that originally it is polarized in one direction or another. However, we'll see that it's actually very symmetrical. We can draw it out, and we'll see that we have 4 chlorines just surrounding that carbon. And in this case, we have a dipole moment out that way, out that way, out that way, and out that way, meaning that they all cancel each other out, which renders this molecule as a whole as not having a dipole moment. So D is going to be our answer.